All right, so we went over how the fixed effect model is of what the fixed effect model is and how that's different from the standard pooled regression, where it just assumes all the coefficients in the regression function is pretty much the same regardless of individuals or time. And in this video, I'm going to go over the random effect model, also called the FGLS model. And we use that so the fixed effect model is essentially saying these differences across individuals or time are not random. And that we must account for these differences because these differences are consistent across individuals or time. But what if these differences actually exist, but they are not very predictable? In other words, they're random. If these differences do become random, then the correlation between x and its errors will be 0. Whereas the fixed effect model, because it's saying it's not random, we have a non-random correlation that's likely to not be 0. And so because of the way the fixed effect model and the random effect model differently accounts for things, we say that the random effect model does not allow endogeneity. Whereas the fixed effect model is saying, hey, these differences are okay and endogeneity will naturally occur because our behavioral or time differences across the panel data is just going to be different since they're not random. All right. Looking at this pooled regression here, we kind of compare it to how we build up the random effect model. And so given this intercept here, we have just a standard estimated intercept regardless of the individual. But then we're also accounting for the variable of u that represents kind of the unpredictable random error. It should still have a mean of 0, but for each individual, it most likely will not be 0. So if we add up that kind of unpredictable randomness plus the unobserved error, which if you ask are pretty similar, but I guess the u is only applicable to the intercept, whereas the error is the error applies to the slope coefficients and variables right here. And so we can combine that into the w variable of what we call the time invariant random error term. So basically accounting for all of the random errors that occurs not only in these slopes, but also here. All right. And so the combination of w comes from u, which we call the unobserved heterogeneity, and then the error, the idiosyncratic error. Again, just these variables differ by what the errors are accounted for. E accounting for here, and then the u accounting for here. So we essentially are saying the random differences across the random effect models is happening everywhere, not just in the slope or the intercept. Some mathematical properties of this variable. We obviously are, when we are calculating the specific value of u, e, or w, we go by expectations. So naturally, the expectation of y and e will be w, and ideally we want that to be 0 because we still want to minimize these error differences that occur in a random effect model. Same thing with the variance. It should follow the property of the idiosyncratic and observed heterogeneity being the equaling the W. And following this, if this part is 0, then the W and then the U, the variance of the random effect model and the U, which is just the intercept, that's going to be equal to each other. And if that happens, then we can concur that the pooled model is the ideal model, because if these are equal to each other and then the error is non-existent, then there is no random effect model or fixed effect model. And then the correlation between these two error components of the unobserved heterogeneity and the idiosyncratic error is given by here. I don't know how we could apply this to real life applications, but I think this is a relatively useful and important formula to know down the road. But right now I have no use for this, so just take it what it is. Alright, so this is kind of the mathematical way of how we can calculate the random effect model. To be honest, I don't have much to say over this stuff. It's kind of, I'm not sure if this should be I'm guessing this should be a minus here, but just a mathematical way of calculating the random effect model where alpha is given by 1 minus all over this, which takes the aspects of the errors, idiosyncratic errors, heterogeneous errors, and then we ultimately get the random effect model where this function effectively minimizes the difference of random differences across time or individuals, and it kind of captures the random differences of a function, the most random function that also minimizes the errors. And it's also important to note that in this process, the time invariant variables, time invariant, so not sensitive to time, not changing over time, these variables are not eliminated, and so we're able to estimate these time invariant variables on y. So basically what it's saying is we can actually make this regression function because these time invariant variables are not eliminated. But I mean, just the intuitiveness of how these mathematical formulas are working, to be honest, I can't really explain that. I don't, in my class when I was taking this, I've never really been tested on like proofs on how this works or intuitively how this works. Kind of just what we should know is how intuitively the fixed effect and the random effect is different. I guess knowing how these variables work, what they mean is nice, but algebraically, I've never been tested on this stuff. Just kind of a good look at how the random effect works mathematically. All right, sorry. Okay. So now we get to the testing between the pooled, fixed, and random effect model. And so for the pooled and fixed effect, we already went through how we can do that, and that is by the f-test. But how can we do it between, the pooled and random, the fixed and random? And so that's what I'm here to cover. So the Lagrange multiplier test, LM test for short, tests whether the unobserved error is significant. So the random error, whether that's significant or not. And so if the null hypothesis that's saying these random errors are not, or doesn't exist. Not random, just the differences alone. So U is given by the unobserved heterogeneity. So just like random errors that can occur in a fixed or random effect model. If we accept this null, then effectively we're saying the pooled effect, in translation, we're saying the pooled effect model is the best for use, while if we reject this, then we will either use the fixed or random effect model. We shouldn't necessarily use the random effect because we don't know if these differences are random or not. We just know that these differences exist. And that's what the LM test is looking at or testing for. But the Hausman test, in contrast, is actually testing if these differences are random or not, because it's testing for endogeneity, which is why Hausman test, it should look familiar because we've covered this over the testing of endogeneity. Mathematically speaking, whether it's testing whether if the correlation or the relation of the x variables in the error is existent or not. And so if we accept a null that says there is no endogeneity, then we use the random effect model because the random effect model does not allow endogeneity. Thus, there is no correlation between these x and errors. Whereas if we reject the null in the Hausman test, then we use the fixed effect model because the correlation between x and e does exist, and so these differences are not random. The way we can test for this, or the way the test works, usually it's done in the software obviously, but it'll calculate the coefficient of the fixed effect model, subtract it from the random effect, and then divide it by the standard error of both the fixed difference by the random effect. But over at panel data, when we're determining which model is ideal, that's what we'll do. We'll test for between the pooled and the fixed using the F test, and then if we we'll test for the pooled and fixed, and then test for the pooled and the random. Remember, for fixed, it accounts for both time differences and individual differences, so we have to account for that. If it accounts for both, we will use the two-way fixed estimator. If we get pooled as our ideal model, then we don't have to worry about any of this. You can just use pooled. But if we reject the LM test, then remember that we must also account for the Hausman test to find out if the REM or the FEM is ideal. If we reject the pooled model with the F test, then we should ideally also reject naturally we should be able to reject the Hausman test as well, because the F test is saying we should use a fixed effect, and then the Hausman test should also agree that we should use a fixed effect model, since I would be guessing that we're testing for the same panel data. All right, that is it for the random effect model test and the tests. Also for the pooled effect model and the fixed effect model. That's pretty much it. In the next video, I'm going to go over binary dependent models.